Look at. Okay, so last time we talked about counting all these various infinite sets, and it always turned out that they were countable. So a person could very naturally think to themselves, okay, well, I get it. They're all infinite. They're all the same size. We're going to find today that that's not so. Again, our sort of medium-term goal here is we want to show that there are more problems in a counting sense. We want to show that there are more problems than there are Turing machines to solve them, than there are algorithms to solve them, than there are programs to solve them. So there must be problems that don't have a mechanical solution. Okay, so we're well on the way towards showing that. And that the technique that we're going to use here to show that there are some sets that have so many elements they can't be counted. That technique is very important in the theory of computation. Technique is called diagonalization, and you'll see why in just a second. Okay, but so the central result here is that there is no onto map from the naturals to the reals. You remember, I'm sure, when we had that array with one-to-one across the top and onto down the bottom, excuse me, down the left side, and we looked at all the possibilities, and we want to show, so the existence of a function says something very important about the sets involved. Was the lesson of that slide. So what we want to show is there is no function. There's no onto function. There is no f from the naturals onto the reals. So this is a case where the lack of existence of a function has something important to say. Okay, it's not possible in an onto way to relate the naturals to the reals. That's to say that the set of reals is not countable. It's infinite, but it is bigger than countable. It is so large you can't count it. Okay, so how do we do that? What's the idea? So let's see. So I'm, as you can tell from having watched some of the videos already, I'm a person who likes to think in terms of kind of sketching out an example. I think that's a big help to get started. Person needs a proof, don't get me wrong, but I think having some idea of where this came from, what it has to do with, is just as important to get started. A lot of times if you have the idea, the proof is easy, but the opposite isn't true. A lot of times if you read the proof, you're still not too sure you understand what the idea is. All right. So enough gabbing, let's talk about it. Suppose that you could count the reals. Why, then you would have some function f that takes in natural numbers and puts out real numbers. So I wrote down some reals, just some pretend reals. I wrote down the decimal expansion of those reals, and I wrote the numbers in such a way that the decimal points line up, just because that's the kind of organization I aspire to. There are some negatives, there's some positives. Some numbers begin with a 0, some numbers begin with a 42. Please, I'm going to look at, in the top row, in row 0, I'm going to look at this initial decimal place. And then in the next row, I'm going to look at the next decimal place. And then in the next row, I'm going to look at the next decimal place. I know you get the idea. And the next decimal place, and the next decimal place, and the next decimal place. That is to say, this is called diagonalization because we're looking at the diagonal. It's no more clever than that. How can I guarantee that I can produce a number that is supposed to be not an onto map? So how can I guarantee that I produce a number not on this list? Why? What I'll do is the number I produce is called z in the proof. The number that I produce will have something other than 3 here. Okay, maybe 1. The number that I produce will have something other than 1 here. 2. The number that I produce will have something other than 4, other than 5, other than 0, other than 1. So I'm going to invent a number that doesn't have a 3. Oh, okay, a 1. Doesn't have a 1. Okay, 2. Like so. I'm going to change all the numbers on the diagonal, and so the number that I'm producing is going to be something that isn't here because it isn't it's not the first row because it's not the first number because it differs in the first entry on the diagonal. It's not the second row because it differs in the second entry. It's not the third decimal entry. It's not the third because it differs in the third. It's not the fourth because it differs in the, etc. That's called diagonalization. Isn't that clever? Isn't that awfully nice? Awfully nice. Okay, so so the proof will say something like, take this 3 and produce the number 1. Write down 0.1. Take this 1, produce the number 2, the digit 2. Now so far, my number is 0.12. Take this 4, and it so happens in the argument, I'm going to turn it into a 1. So far I have 0.121. And in fact, all the digits that aren't 1s, I'll turn into, all the digits that aren't 1s, I'll turn into 1s. And if I have a 1, like there or there, I'll turn it into a 2. So I will get 0. Let's see if I can do it right. There we go, 0.121, 1, 1, 2, etc. 0.121, 1, 1, 2, etc. And I'll claim that that number is not any of the numbers on this list. It's not any of the numbers on the list because it differs in the first decimal place, differs in the second decimal place, differs in, it's not the nth number on the list because it differs, you know, in the associated decimal place, n plus what the decimal place. Okay, so it's not on the list. Isn't that interesting? Isn't that interesting? Okay, anyway, so here we go. So we're going to show that no map from the naturals to the reals is onto, and we're going to use the idea that's written up there, and it's just a question of writing it down in some sensible way. So you denote the ith decimal place here of f of n by f of n square brackets I. I just made it up. That's not a standard notation or anything. I just made it up. So the ith decimal place of f of n is f of n square brackets I. If f is a number with 2 decimal representations, then we can use the one ending in zeros. Now, this is the only tricky point of the argument, and it comes right now, right in the early on in the argument. Yeah, I got left a stray mark behind there. Come on, come to Papa. There, God, making it worse. Oh, because I was pressing on the wrong button. Okay, so there are some numbers that have 2 decimal representations. For example, 0.1. 9 equals 0.2000 ... Because how do I know they're the same? Because, well, the answer is they're the same because they differ by less than 1/100th. They differ by less than 1/1000th. They differ by less than 1/10,000th, etc. So they differ by less than any number you give, so they must be equal. Wow, so in other words, a number can have 2 different ways you can write it. It's almost as though I had 2 names. It's almost as though you could call me Jim, or you could call me my social security number, which I'm not going to tell you. Almost as though. All right, still same number, 2 different representations. But that throws a little monkey wrench in this idea because you say, well, all right, so you came up with a number you came up with a representation that's not on the list. Well, so what? You know, maybe on the list, maybe that the number's on the list, but this particular representation isn't on the list. Okay, but all we have to do is be a little bit careful, is that numbers have 2 representations in decimals if and only if one of them ends in 9 and the other one ends in zeros. So the only way you can have 2 representations is if you end in 9s, is if one of the 2 representations ends in 9s. So all we got to do is avoid this ending in 9 nonsense. And now that's exactly what happens here, is that I don't ever deal with 9s and zeros, I deal with 1s and 2s. So the number that I produce is going to deal with 1s and 2s, no 9s and zeros, so I never have to worry about the dual representation issue because in decimal it only happens with 9s and zeros. Okay, so you let G take that G of J is 2 when J is 1, and G of J is 1 otherwise. So in other words, you switch all up here in the array, you switch all of the numbers to a 1 if they're not a 1. But if it is a 1, you switch it to a 2. No 9s and zeros. Problem goes away. All right. Anyway, back to the proof. So now you let Z be the real number that has 0 to the left of its decimal point and whose ith decimal digit is G of, it's a little difficult to write down. It's not hard to understand, difficult to write down. G of F of I, the ith decimal place. Anyway, so what you have there is that z is not equal to f of I for the reason that we saw up here. This number is not the thing in the first row because it differs in this decimal place. It's not the thing in the second row because it differs in this decimal place. And we don't have this dual representation problem. So the argument goes through. Isn't that nice? F is not onto because we produced a number that F does not output. Isn't that nice? Awfully nice argument. Very, very pretty. One of those things where you say to yourself, I'm glad I study mathematics because there are such nice things. Okay, so we find that there are sets that are so big. The real numbers is an example. Sets that are so big that they can't be counted. You can start counting and you can count infinitely many of the elements, but you never can count them all. Okay, with the natural numbers. So a set that's infinite but not countable is called uncountable. Listen, just a name, it's not a very clever one. So we can adjust the argument that was above to show there's no onto function from n to lots of other sets, and I named 2 in particular. You could do the positive reals, just don't worry about the negatives, or 0. Or you could do the interval between 0 and 1. Okay, whatever's convenient for you. So there's lots and lots of other sets that are uncountable besides just the reals. In particular, you could look at the interval from 0 to 1 here, and you can say that it is can look at the interval from 0 to 1, and you can say that it's got a finite extent, whereas the reals had infinite extent. All the way down to negative infinity, all the way up to plus infinity. But S has only finite extent. So in fact, you can have uncountable sets that have only finite extent. Anyways, all kinds of interesting things here. We're focused on Turing machines, so we're going to push that particular aspect of it. But there's all kinds of interesting things to think about here. Okay. So what we have is that some sets are actually bigger than others, some infinite sets are actually bigger than others. So okay, so fair enough. So now I have that a set S has cardinality less than or equal to a set T. If there's a one-to-one function from S to T, not necessarily onto one-to-one. And just some quick examples. So we have that the set I wrote down in words 0, 1, 2, and the set 0, 1, 2, 3. And obviously you can find a map that takes S to T because you take the word 0 to 0, you take the word 1 to 1, and the word 2 to 2, and that's clearly a one-to-one function. It happens not to be onto, but anyway, it's one-to-one. So the cardinality of S is less than or equal to the cardinality of T. In fact, it's strictly less, but anyway, it's less than or equal to. If you take S to be the even numbers, 0, 2, 4, then the injection map, injection just means that you shove it in there where you think it goes, taking S to N, given by S goes to S, that's the definition of injection map. S goes to S there, it's an embedding, is one-to-one. So the cardinality of S is less than or equal to the cardinality of N. Right, injection is another word for one-to-one map. Okay. Here you fix 2 intervals of real numbers, the interval from 0 to 4, including the 0, not including the 4, and the interval from 1 to 4, including the 1, but not including the 4. And again, here we can show that, oops, I have this reversed. We can show that, I should have written here T equals, I'm sorry, little typo, T equals, and I should have written here T less than or equal to S. The cardinality of T is less than or equal to the cardinality of S. I'm sorry, I simply mistyped. I apologize. Okay, and similarly, the cardinality of the naturals is less than or equal to the cardinality of the reals, and that's in fact the larger point of the whole argument that we're doing. Is that those things which are counted, which can be counted, has a cardinality less than or equal to, in fact, strictly less than the cardinality of the real numbers. Things which can be counted are fewer than the things which are associated with the real numbers, which have the same cardinality as the reals. Okay, and we already know that Turing machines can be counted. Okay, so Cantor's theorem says for the next result, I want to recall that a characteristic function of a Boolean, a characteristic function 1s, and there we go. 1s is the Boolean function determining membership. That is to say that 1s returns a 1 if little s is in capital S, and 1s returns a 0 if little s is not in capital S. So it's just the Boolean function that gives you membership. And Cantor's theorem says a set's cardinality is strictly less than that of its power set. The cardinality of a set is strictly less than the cardinality of its power set. And again, a person can at this point be saying, like, wait, I signed up for this for the theory of computation. Where is this going exactly? So the answer is we know that the Turing machines have the same cardinality as the natural numbers. We know that there are as many Turing machines as there are natural numbers. We know that. And I'm going to show you that there are as many problems as there are real numbers, as there are power set of the naturals, as there are real numbers. In this particular case, we're going to take that. Okay, so that's what it has to do with. That's what it has to do with theory of computation. And the harder half is showing that no map from S to the power set of S is onto. So as an example here, let's consider the set that consists of 3 elements, and I'm going to look at a particular function from S to its power set. So this shows that the set's cardinality is strictly less than its power set. So I'm going to show that there is no one-to-one, no onto map from S to its power set, because I'm going to imagine a map from S to its power set and show that it can't be onto. And it's just going to use the diagonalization technique. That's all. So let's give it a whack here. So imagine that I have S. So F has to take as input the elements of capital S, little a, little b, and little c. And when you make up one of these examples, you just try to make one up that's pretty generic, that isn't especially, you don't want to have any special cases. You just try to make up kind of junk cases. So I put, in the power set, I took BC, B, and ABC, just to take some. Okay, so I looked at what happens here for the elements of capital S, and this is the set BC. This is what happens when you take the set BC and you apply this is f of little a. F of little a is the set does not contain an A, does contain a B, does contain a C. F of little b does not contain an A, does contain a B, does not contain a C. F of little c does contain an A, does contain a B, does contain a C. Okay, so once again with the top line, f of little a, this f right here, f of little a does not contain an A. That's what it says here. When you apply the characteristic function on f of little a to a, you get no. When you apply the characteristic function f of little a to b, you get yes. When you apply the characteristic function f on f of little a to c, you get yes. And now you've seen the diagonalization trick. All we got to do is produce a set, an element of the power set, that where you flip that 0, you flip that 1, and you flip that 1. That is to say, I'm going to produce a set that contains A, because you flip that 0 to a 1, meaning yes. So the characteristic function of the set I'm producing is yes, going to contain an A, is no, not going to contain a B, and is no, not going to contain a C. And I regret the comma now, and I'm just looking at closing curly braces. Okay? So I'm going to produce here the set, capital R is just contains an A. And capital R is not the output of the function f. Capital R, this set right here that I got from diagonalizing down this table, is not f of little a, it's not f of little b, and it's not f of little c. So so the function f is not onto, because I've produced a set that is not in its range. Okay, so that's the idea there, is that I'm going to do the same diagonalization trick that we just saw a minute ago, only now I'm doing it with these sets. So the argument is just basically what we just did here. So half of the argument is easy. It's easy to see that you can just map S into the power set by taking, for example, iota of S is the set singleton S. And that's clearly one-to-one. So we get that the cardinality of capital S is less than or equal to the cardinality of the power set of capital S. Okay. For the other half, the other half that we've illustrated above, the other half to show that no map from a set to its power set is onto, we're going to fix any function, and I'm going to show that it is not onto. And so I'm going to produce a set here that isn't in, that I'm going to produce a set that is not f of little s0 or f of little s1 or f of little s2. So this is not in the range of f. This set right here, capital R, is not in the range of f. And it's just simply the set we constructed in the prior slide. You make it contain all of those things. You make it contain all of those things that are not elements of little f of itself. Now we saw that on the prior slide. I looked, there we go, losing my mouse, there we go. We on the prior slide here, we looked at, we looked at f of little a, and we said, is little a in f of little a? No? Okay, then throw it in here. Is b in f of b? Yes. Don't throw it in here. Is c in f of c? Yes. Don't throw it in here. So whatever happened, we did the opposite. A not in, throw it in. B in, don't throw it in. C in, don't throw it in. Whatever happened, we did the opposite. Okay, all right. Okay, so now we, whoops, I keep losing my mouse. I apologize. There we go. So, so now when we went to produce this set, we just did the opposite. When you write down what we did, we looked to see whether s, little s is an element of f of s, and we did the opposite. Put it in if it isn't, don't put it in if it is. And then the verification that produces a set capital R is not indeed equal to f of little s for any little s is pretty straightforward. Okay. In particular, that you want to note this that I underlined is exactly where the bits get flipped. So just to do an example, because again, some of these things have a way of seeming awful abstract. So if I take the set S of little a, little b, S equals little a, little b, then that has a smaller cardinality than its power set. The power set consists of these four things. Size 2, size 4, smaller cardinality. Now that's not infinite, but nonetheless, 2, 4, smaller cardinality. Let's go to infinite. So let's look at all the subsets of the naturals. All the subsets of the naturals, it's a collection, so I called it C. All the subsets of the naturals, there we go. I don't know, 1, 2, 6 is a perfectly good finite subset of the naturals. 0, 1, 4, 9 is a perfectly good infinite subset of the naturals. All the subsets of the naturals are here. That set, by the lemma above, by Cantor's proof, that set has a larger, strictly larger cardinality than the naturals. Okay, so the power set of the naturals has a strictly larger cardinality than the naturals. And again, we're just about there. Here we go. There are sets that cannot be computed. So we're back to thinking about theory of computation. So wait, you know, we went on a bit of a ride here, but now we came back to what it is that is our central interest in the course, what can and can't be computed. So let capital F be the set of functions from the naturals to the naturals. Let capital F be the set of functions from the naturals to the naturals. The cardinality of the set, the naturals, is strictly less than the cardinality of the set capital F, and the answer is there's a one-to-one map from the power set of the naturals to capital F. There's a one-to-one map from the power set of the naturals to capital F. You just simply associate each subset S with its characteristic function. Oops, I made a stray mark there. You associate each set with its characteristic function. So, for example, from the prior slide, when you had the set 1, 2, 6. Okay, well, the characteristic function of that is the function that maps 0 to 0, maps 1 to 1, maps 2 to 1, maps 3 to 0, maps 4 to 0, maps 5 to 0, maps 6 to 1. In other words, it only returns 1 when you're an element of the set. That's the characteristic function. Okay, so we're going to associate each set with its characteristic function. So we're trying to find a map here. We're trying to find a map that that associates here subsets of the naturals with functions. And our map is going to be, given a subset of the natural, you connect it in your mind with its characteristic function. So that it does indeed take in natural numbers. It's going to be taking sets of natural numbers and then puts out puts out functions. So for each subset, it puts out a function. So we know that the cardinality of the natural numbers is strictly less than the cardinality of the power set of the naturals, and that is less than or equal to the cardinality of f because we just produced a one-to-one function between the power set and f. Okay, so the cardinality of the naturals is strictly less than the cardinality of f. And what is this? It seems, again, awful abstract. What does this have to do with Turing machines? Compute functions from the naturals to the naturals. So we think of a problem as being, what do Turing machines try to solve? They try to find the appropriate function. You say, well, I got to write a program that does. The Turing machines try to find the appropriate behavior, try to find the appropriate function. So problem must be a function from the naturals to the naturals. We've just shown that there are uncountably many such problems, uncountably many functions from the naturals to the naturals. But there's only countably many Turing machines. So again, I know that it seems to go off into infinite sets and it seems to get awfully abstract, but the nut of what we've done is we've shown there are uncountably many problems. Turing machines solve a certain kind of problem. There are uncountably many of them, but only countably many Turing machines. There are strictly fewer many Turing machines than there are strictly fewer many Turing machines than there are problems. There are lots of problems, not so many Turing machines. Lots of problems, not so many Turing machines. So this should remind you of the child's game of musical chairs. I just make sure that everybody remembers what musical chairs is. Musical chairs, you might start with 6 children, and you might have 5 chairs. I can't make 5 chairs. 2, 3, 4, 5, and 6 children. 1, 2, 3, 4, 5, 6. And it's called musical chairs because the children, you play some music, dun, 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 and the children walk around, and then all of a sudden you make the music stop, and the children have to try to grab a chair. And of course, there's 6 children, 5 chairs. There are more children than there are chairs. Some child goes without a chair. I don't know which child it is. Maybe it's this guy, maybe it's this guy. I don't know. But some child goes without a chair. It's just a counting argument. There are fewer chairs than children. Some child goes without a chair. So that's what we've got here. There's a smaller number of chairs than children. So some children are left without a chair. There's a smaller number of Turing machines than there are functions from the naturals to the naturals. So some functions from the natural to the naturals are left without a Turing machine to solve them. I don't know right away which one it is, but some functions are left without a Turing machine to solve them. So there are some functions from the naturals to the naturals with no associated Turing machine. There are jobs that no computer program can solve. Now, again, I get that we've gone sort of into an abstract zone, although there's a lot of stuff that we needed along the way, like numbering Turing machines that we're going to keep using as we move throughout the course. But we kind of went into an abstract zone, and so just to try to summarize, we've shown that there are problems no Turing machine, no computer program will take Church's thesis. No Turing machine, no mechanical device can solve. Now, a person can ask, very fairly ask, well, but you gave a purely unconstructive proof. You gave a proof that didn't show me how to come up with such a problem, and so I'm not sure what to do with that information. I mean, it's as though you went to the auto repair shop to have your car fixed, and you showed up at the end of the day, and the person said, well, your car does have a problem, but won't tell you what it is. I mean, how is that useful? But of course it's better than nothing. But maybe a person who has the spirit of this course would be a little frustrated that it isn't something you can find. So the next job is to produce a specific problem that you cannot solve. We'll absolutely do that. But at the moment, leaving the day today, we have shown that there are jobs no Turing machine, no computer program can do. And of course, that's a big step. Knowing that there are jobs without a solution is a first step toward understanding which jobs. Okay, great. Bye-bye.